Hi, everybody. I am Carly Benhar-Kukula. I am, one moment. My name is Carly Benhar-Kukula. I am the Women in Transportation Fellow. Hello and welcome to the Traffic 21 Mobility 21 University Transportation Center's Deployment Partner Consortium Symposium, Research and Education Showcase. The Traffic 21 Mobility 21 Deployment Partner Consortium is engaged for identifying real-world transportation needs, research project development and deployment, technology licensing and commercialization, student recruitment for jobs and internships, class and capstone projects. Putting our research, development, and deployment approach into action, this annual symposium provides an opportunity for interaction and discussion among researchers, students, and deployment partners. Please note this session is being recorded, and all participants' microphones are muted. We will have an opportunity after the presentations to ask questions and engage in discussion by joining a breakout room where you can talk directly with the presenters. You can also add comments to a virtual idea board. Directions will be posted in the chat. Now I would like to introduce this session's speakers and the topics they will be discussing with us. From 11 a.m. to noon, we had autonomous logistics services, spectrum policy for connected vehicles, real-time obstacle detection and traffic analytics, development of a safe, profitable, and fair robotaxi deployment strategy, and INCEPT software for determining optimal placement for electric vehicle chargers. The session that will be starting now is estimating traffic volumes from bus-based video imagery obtained during regular transit operations, presented by Mark McCord. Towards More Accessible Trip Planning Dialog System by Maxine Eskenazi, and Bus on the Edge, Continuous Monitoring of Traffic and Infrastructure by Christoph Mertz. And presenting Mobility Data Analytics Center, we will have Ran Yao presenting Sean Chen's poster. And one moment, please. We will have school bus sharing, our final presentation for this block, with Peter Zhang and Hao Xiao. Thank you. And please, let's get started.
Thank you so much, Carly. We're glad that you're able to be here today. We're going to get this session kicked off with Mark McCord. Mark, would you like to start sharing your screen and tell us about your project?
How's that? So, is there?
Perfect.
Great, you can hear me.
Yes. Yes,
great, thanks. Yep. I'm Mark McCord, and I'll be presenting this work that my co-investigators for Bia Michelani and Benjamin Koifman are involved with, where we're trying to take advantage of video that's already being collected on buses for other purposes, while the buses are out there doing their normal operations to estimate traffic flows. Just try to give you a high level. We can talk more about it in the breakout rooms later on if we want to. The motivation, of course, is that the motivation for this project is traffic volumes. How many vehicles are on your roadway segment are used for a variety of transportation planning operations applications. In the traditional way we do it, we either put a person out there by the side of the road and count vehicles as they go by, or we stretch out a road tube that counts vehicles as they go over the road tube, and we get data through time, but only at very specific limited locations, and we only do it on an infrequent basis. Buses, on the other hand, go all over your urban network, so they have the potential of being sensor platforms that can get information on traffic all over the city, not only at specific locations, But of course, because they're moving, they're going to get very short duration observations. But the nice thing that, sort of came around is buses are putting cameras on, transit agencies are putting cameras on their buses for other purpose, liability, if there's an accident, who's at fault, safety, if there's a hijacking or something, can we see someone? And we came up with the idea that since those cameras are already out there looking out on, they're looking in the bus, they're looking outside the bus, we see vehicles, can we take advantage of this information that's already being available in this imagery and turn it into traffic volumes? We don't have to pay for the sensors, we don't have to pay for the platforms, it's already available. So the idea is to take advantage of this available information, this available video imagery, to estimate traffic volumes across our network on an ongoing basis. That concept's somewhat straightforward, but let's just see if, the project's about, does it work? Now, I won't go into the details at this time, but this is supposed to be an eyeball of an observer. In that first slide, we showed you people counting vehicles passing a segment, a point in the road, or a road tube counting vehicles as they go over the road tube. That's the traditional estimate of traffic volumes, traditional definition of traffic volumes. The bus, on the other hand, is moving in one direction while the vehicles are moving in another direction. So it's sort of a different paradigm. In the literature, they called it moving observer, but we had to modify the traditional approach to be able to work for our application, where buses are going one way, vehicles are going another way, buses then go somewhere else and only come back a lot later. So I won't go to the simple, at least our first cut simple methodology to estimate from one bus pass going over the roadway, how many vehicles per hour, for example, would we estimate at this fixed location. But we have a simple approach. We're going to see how it works, and our research is about fine-tuning that approach and other pieces of that. How do we do it right now? Well, right now, these are images from the bus. And so we see the vehicle coming, and we've developed a simple GUI, graphic user interface. And when the vehicle passes, we just click it. Then we have all these clicks that we can convert into the information we need for our estimate of how many vehicles are passing a spot on the road per unit time, which is our estimate of volume. And we've done several empirical studies. I'll just illustrate with this one. This is a network across the Ohio State University campus. We get the imagery from Ohio State University buses. We have good relations with them, so they give us the video. This was from October 2018. We repeated in 2019. We're repeating it right now in 2020. Volumes from 7 a.m. to 7 p.m. The MORPC, the Mid-Ohio Regional Planning Commission, who's our local MPO, Metropolitan Planning Organization, laid road tubes out on several segments in our roadway. We got buses going all over the place on this roadway for this 12-hour period. We converted the bus imagery into our estimates of volumes. And in this not simple, but this first empirical result, we're sort of showing, for example, our video estimates were 275 vehicles between 7 a.m. and 8 a.m. On this roadway segment in this direction. The road tube said 278. We calculated our 275 volumes from 3 buses going over that roadway segment in that 1 hour period. We did that 10 different segments, 12 different hours, so we had 120 comparisons. But we also said how many vehicles traveled on this segment over that 12-hour period, and we got 5,147 from our video, 5,227 from the road tubes. We calculate how different they are, and the moral of the story is, if we look at the specific hour, they don't do that great, but if we look at the 12-hour, it looks pretty good. We're getting close to about 10% differences, which is what usually people in traffic monitoring are targeting. Some segments do a lot better than others. We're looking into those proportions now. Vehicle miles traveled tell you how many vehicles travel on your overall roadway segment or overall roadway network. We're getting down when we do that to only like 3% errors, which is really pretty good. In addition, we use these vehicle miles traveled. We give them to the OSU planners and operators so they can do their sustainability modeling. We do that on an ongoing basis. And we can talk about in the breakout room if we want the ongoing research components that we're looking at, including can we do the vehicle detection automatically. So you can read the summary, but basically we've got this method, we've got results, they're looking pretty good, we're trying to improve it, but we're also using the results now in an outreach function. So I'll stop there, turn it back to Lisa Kay. Or is it Carly who's taken over here?
Nope, you still have me, Mark.
Okay, good.
So much for that. If you can go ahead and stop sharing your screen, I'm going to ask Yulan to go ahead and start sharing her screen. As you mentioned, we will be having opportunities for more conversation. So it's great that we kind of get the overview and then we'll have more conversation. Our next presenter, Yulan, is going to be presenting on Maxine Eskenazi's project called Towards More Accessible Trip Planning Dialog System. Yulan?
Yes. Can you see my screen?
We can, and we can hear you just fine.
Okay. Today, I would like to introduce you to the mobility mode in CMU Get Going. CMU Get Going is a local trip planning dialog system that provides public transit, driving, and walking directions in the Western Pennsylvania area. It is available over a local phone line, and it was initially designed tailored to the needs of older adults. In development of the new mobility mode, we collaborated with Passview, a local startup that focuses on pedestrian accessibility. They help users navigate sidewalks faster and safer without barriers. In this mobility mode, we provide detailed walking directions with various accessibility modes depending on user needs. This includes users with low vision, wheelchair users, and cane users. Here's a short demo of the system in wheelchair mode, where a user wants to go to Pittsburgh Paints Arena from CMU.
Welcome to CMU Get Going. How would you like to travel today? I can give you public transit directions or walking directions.
Public transit.
Great. I will provide you with directions to your destination by public transit. Where are you going?
PPG Paints Arena.
Okay, going to PPG Paints Arena. Where do you want to leave from?
CMU.
Okay, leaving from Carnegie Mellon University. When do you want to travel?
At 2 p.m.
Okay, traveling at 2 p.m. Would you like me to pause after every step to give you time to write things down?
Yes, please.
Okay, great. Feel free to ask me to repeat a step if you didn't catch it the first time. Just a minute. Let me look up the directions. You are now hearing the default Google directions. To hear a route in mobility mode, please say alternate route. The amount of time your trip will take is approximately 18 minutes, and you will take one bus. Let me know when you are ready for the next step.
Yes, next step.
The first thing that you want to do is to walk for about 3 minutes to Forbes Avenue at Craig Street. Shall I proceed?
Yeah, continue.
Next, you should take the 61C to 5th Avenue McGee Street. It will depart at 2:04 p.m. Let me know when you are ready for the next step.
Next step.
The final step is to walk for about 1 minute to 1001 Fifth Avenue. Please tell me when it's okay to continue.
Alternate route.
You are now hearing the mobility wheelchair mode. The amount of time your trip will take is approximately 18 minutes, and you will take 1 bus. Shall I proceed?
Continue.
The first thing that you want to do is to start at Carnegie Mellon University. Go west on Forbes Avenue towards South Craig Street, and then cross the street at South Craig Street. Shall I proceed?
Next step.
Next, you should turn right on South Craig Street. Shall I proceed?
Continue.
Next, you should turn right on Forbes Avenue and finish at Forbes Avenue at Craig Street on the right. Shall I proceed?
Yes, continue.
Next, you should take the 61C to 5th Avenue McGee Street. It will depart at 2:04 p.m. Please tell me when it's okay to continue.
Continue.
Next, you should start at 5th Avenue McGee Street, go west on 5th Avenue toward McGee Street, and then cross the street at McGee Street. Please tell me when it's okay to continue.
Next step.
The final step is to continue on 5th Avenue and finish at PPG Paint Salon on the right.
In the previous example, starting from the main entrance of CMU to the bus stop, we have 2 choices: to cross the street on Moorwood or on South Creek. This picture shows the intersection of Moorwood and Forbes Avenue. Here, there is construction going on across the street.
Go west on Forbes Avenue towards South Craig Street.
So the system asks the user to go west first instead of cross the street here. Once we have walked to South Craig Street,
and then cross the street on South Craig Street,
we can now safely cross the street.
Next, you should turn right on Forbes Avenue.
Then after cross the street and turn right, we are at the bus stop. This accessibility information used to be only available on graphical user interface. We did a lot of modifications to incorporate this information into audio format. This includes using natural language generation techniques to transfer information that are structured data into natural language representations. We also did address conversion to and from geographical coordinates and resolved abbreviations and acronyms in address so that they are more understandable over the phone. So after all these changes, we have delivered a system that can be used over the phone by users with various mobility issues. Now the walking routes are more accessible for visually impaired users, and other users can focus on using their wheelchairs, scooters, and walkers while navigating themselves. If you are interested in our system, you can visit our website, call the system yourself, or send me an email. So here's the end of our presentation. If you have any questions, I'll be happy to answer them in the breakout session later.
Thank you so much, Yulan. I think there's going to be some interesting conversation that's going to be coming in our breakout sessions today. Next up, Christoph Mertz is going to be talking about his project, Bus on the Edge, continuous monitoring of traffic and infrastructure. Christoph? Oh, we're not hearing you.
Okay, let's try this again. Okay, can you hear me and can you see me? Okay, okay. So bus on the edge, continuous monitoring of traffic and infrastructure. Actually, the presentation, the two presentations before me already mentioned, there are transit buses now with which have cameras on the side, and with those cameras you can observe what is going around the bus. So what we have been working on for the last 2 to 3 years is actually getting the edge computing up and running, with which you do calculations or where you can take that video streams, actually 5 video streams from a bus, analyze them on the bus itself to find interesting events, interesting objects, interesting things you can see there, and then send them to a, I don't know, traffic management system or somewhere else. So there's a lot of nitty-gritty computational edge computing stuff, but the important thing is that we can then, from a central location, program the bus to look at specific things, so the traffic count, which was mentioned earlier, would, for example, be one thing which could be running on it. But I will show here like 3 examples which we want to run on it. So one is a traffic count. So here you can see how we are driving along. Now, this is not the bus. This is a normal car with a smartphone on it. But you can see how we can track consistently the traffic on the left side. But what we also want to do is look at the parked cars. So parked cars is also an interesting data statistics because cities, townships, they do want to manage their parking. So you want to know like how much parking there is, how much there's available, maybe as a user to see if you can go there and actually find a parking spot, or for the city planners to know if there's enough or not enough. Also, on this particular street, you're not allowed to park on the right side during rush hours. So that's a traffic management issue. And you want to see, you know, what's the compliance. If you say, so like here, there are signs up like between 4 and 6 o'clock, you're not allowed to park. What's the compliance? What's the best time to do that? So this kind of, what we want to do is create those traffic statistics that then somebody else can use them and analyze and optimize parking, traffic, and so on. So that's one application. Next thing is landslides. So landslide is a big problem here in this area of United States, in southwestern Pennsylvania. If you've been around long enough, like 2 years ago was a very bad year because there was a lot of rain, and with the red soil here in these areas, red soil, water, and lots of hills create a lot of landslides. And here's just an example of one area which I go regularly to take pictures and see how this landslide develops. You see it over several months from just some cracks, which are like parallel to the road, to actually it cracking in here so bad that they had to put big signs up there so that nobody is driving over it. So this is something also we want to do on the bus, observe areas where there might be landslides, and then do early warning, or if it happens very quickly, that we can do a post-event analysis. And here, yet another one application. Now this is HD map update. This is something we're actually doing with Argo together. So for autonomous driving, one important thing is the maps. And it's not just your regular Google or Apple or whatever map. You want a high definition map, That is, you want to know exactly where the road is, where the lane markings are, where the traffic signs are, like within a few centimeters. And so those companies, they do send out their cars with laser scanners and cameras and create these maps. So it's very expensive, but with the maps, you know, they're outdated very quickly. So you need to constantly update them. And it would be really way too expensive to continuously drive with those expensive cars to update it. So what we want to do is take these buses, when they drive around, they take pictures, compare it with the current HD map, and see if something has changed. And what you see here is just basically the algorithm which we're going to run is, so you have those images, new images. In this case, we'll look at the traffic signs. You detect the traffic signs, then you take this image and localize it within the map. So you see these red boxes here are actually the original images taken by the expensive vehicle, the Argo vehicle. And here, these little boxes are the images taken, well, in this case, our car, but then eventually by the bus. We can align them with using computer vision and compare it. And then here, in this case, this sign was already there, so we mark it blue, and this sign is new. So we mark it red and then say, okay, here at this location is a new sign. So this way you can update the map. And we want to not just do the traffic signs, but lane markings or anything else that is relevant for the autonomous driving.
Christoph, I'm gonna just interject you. The 1 minute warning.
Okay, I'm at my last slide.
Okay.
So good. So here's again in the overview, and actually for anybody who's here, I actually want to know what you want us to detect. So if you have any application, if you have any data you would like, any ideas you have, please let me know. I would be happy to discuss that with you and have more applications on the bus. So thank you very much.
Thank you so much, Christoph. I know there's so much to talk about, and it's hard to contain ourselves in a short period of time. If you can go ahead and unshare your screen.
Yep.
I'm going to ask Yulan to go ahead and share your screen. He is going to be talking today about the Mobility Data Analytics Center that Chen leads.
Hey, are you able to see my slides?
We sure can, and we hear you just fine.
Cool. Hello, everyone. My name is Yulan. I'm a fourth-year PhD student in Department of Civil and Environmental Engineering at Carnegie Mellon. I'm currently doing research in Mobility Data Analytics Center, which is advised by Dr. Chen. I'll briefly describe the research goals of our lab and demonstrate why our team is very suitable for developing AI for smart mobility, and also the ongoing projects currently in our lab. So our current research goal is to inform smart mobility decisions with machine learning and AI. The transportation systems always involve complex travelers, also the high-dimensional network flow dynamics. So data collected over the years is often very sparse, like spatially temporally sparse. So the data-driven approach alone can't generalize very well to the non-recurrent traffic conditions, which are actually the actual operation bottleneck of most TMCs in US. So our approach is to connect the computational science, the physics of the network modeling, together with machine learning, and we believe this incorporation is the best choice for informing smart mobility decisions. We really have a perfect configuration for developing AI for smart mobility, and I have two reasons to show you guys. The number one is we have a very strong team. Our lab has 10 PhDs and 1 postdoc. all have a strong knowledge of physics-based transportation network modeling, while most of us also pursuing an advanced degree in machine learning at CMU. We've already developed the backbone physics-based traffic simulation models, and we're ready to incorporate machine learning at any different levels of hierarchies in the physics-based model. The number two is our lab has collected like large amounts of multi-source traffic sensing data with dense spatial temperature coverage over the last 10 years. We have shapefiles, we have real-time traffic data, events, public and transit data. We also have parking transactions, also different kinds of crowdsourced data. Together, like with these two reasons, these two like make it possible for our lab to precisely prescribe mobility decisions with physics-informed machine learning approach. Here are some feature projects our lab has done recently, and most of them can be categorized into like two types. One is the real-time traffic management. It automates the analytics process of the TMCs and prescribe the optimal policy ahead of time. So the real-time predictive traffic management platform, the Philadelphia region real-time traffic management platform, and also the high resolution traffic sensing with autonomous vehicles belong to this type. The other type of research our group are currently doing is to recommend long-term infrastructure design and policies to public transportation agencies. First and last mile mobility services, and also the optimal design of high-frequency public transit system, as well as crash hotspot and cause analysis. These three projects belong to this category. I'll briefly describe two projects. The first one is the real-time predictive traffic management platform. So basically, our solution to the Cranberry Township TMC is to build an early intervention system which recommends the optimal signal timing plans 30 minutes ahead under real-time traffic incidents. The highlight of this project is basically we fuse a Visum traffic simulation model inside of a neural network, which makes it generalized to the non-recurrent incidents happening on the network. And we are able to recommend the optimal signal timing 30 minutes ahead to the TMCs, and they then can try to see if this signal timing can alleviate the traffic anomalies on the network or not. This our platform has already been deployed at Cranberry Township for almost a year, and the field trials from the feedbacks from the traffic operators, they tell us that after deployment of our models, their engagement of the incident signal timings are engaged like 15 to 20 minutes ahead. And here's like a demo I want to share to you guys. I think it's here. So this is the dynamic dashboard we've developed for Cranberry Township. It's able to detect the potential traffic anomalies in this local network and recommend the optimal signal timings to alleviate these anomalies 30 minutes ahead. And the real-time traffic predictions are shown here, and also there's a like animation which shows what happens in the next 30 minutes. Right, let's get back to the slides.
And just a 1-minute warning for you.
I see. So the second, this is like a different approach we apply for the Philadelphia region. It's physics-based simulation model. We can incorporate machine learning to different hierarchies in this model, from origin destination estimation to travelers modeling. And we've developed an interactive dashboard for TMCs to optimize their DMS messages shown on the highway. And this is actually my last slide. I want to thank you all for staying with me, and we look forward to collaborating or more like deployment partners to apply our research to develop the infrastructure systems in US. And if you want to know more details about the ongoing research, you can go to our breakout room or visit our website or just send emails to Dr. Sean, our lab director. Thanks. I think that's it for my presentation.
Thank you very much. And if you can go ahead and stop sharing your screen. How, if you would like to start sharing your screen, you're going to be sharing with us the school bus sharing project that Peter Zhang is the PI for. Go ahead, Hao.
Okay, great. Thank you, Lisa. So my name is Hao. I'm currently a master's student in the Department of Civil Engineering at Carnegie Mellon. And this work is done in collaboration with Zihan Li, Neha, Professor Haivang, and Professor Peter Zhang at SAMU. So first, I'll give a brief background on the bus transit system in the US. So there are over 500,000 buses transporting 25 million students daily to and from schools in the United States. And this transit system is actually one of the largest mass transit system in the country. However, the per student transportation cost is currently at roughly $2,000 per student per year. And this high cost is due to the increasing hardware cost, for example, the maintenance cost of the bus's fleet. And also the current bus routing are often designed suboptimally, which results in long bus riding time and high cost. And in addition, in this multi-school transit system, the routing decisions are usually made individually by each school, without leveraging the benefit of route sharing among multiple schools. And to solve these challenges, we defined the school bus routing problem with collaboration. And the aim is to generate optimum routes and schedules for each bus while allowing collaborations across multiple schools. And also our end goal is to minimize the number of buses required and also to minimize the total travel time for all the students. And we decomposed our problem into three main problems with increasing complexity. First, we wish to learn the routing problem for each school without collaboration. Then we'll move on to collaborative school bus routing. And finally, we will introduce an online learning method, which takes sequential input and computational feasibly solve the traveling salesman problem. And I'll start with the first problem, the routing problem without collaboration. In this problem, we need to make three decisions simultaneously. The first one is to select the subset of stops to visit among all the potential stops. And the second decision is to assign each student to a stop. And finally, we need to generate the optimum routing for each bus under the several constraints while minimizing the total travel time. And the figure below captures an instance of the routing problem and its solution. I'm just gonna briefly show our approach for solving the problem. If we look at the objective function, which we try to minimize, the first term is the so-called routing cost, which is a function of total of stops selected. And the second term is the total travel distance, which we wish to minimize. And the beta parameter controls the trade-off between the two objectives. So for example, when beta is large, the student will be assigned to the nearest stops to their home. And for a small beta value, students may work longer in order to consolidate several stops and to lower the routing cost. And this trade-off is shown by the parental frontier below. And moving on to the next question, which is the collaborative school routing problem. additional to the previous problem, the problem now introduced two additional complexities. First is relaxation. So the fleet of buses can now be shared between both schools. And there's an additional constraint. So each student now applies a pickup and delivery constraint, which ensures the student is transported to and from the designated school. And this is an instance of the collaborative school bus routing, which we solved by an algorithm called taboo search. And the table shows the benefit of collaboration. So with collaboration, we're able to reduce the number of buses required in this instance from 8 to 6 and reduce the total distance traveled by 21.2%. And finally, to further solve the collaborative routing problem, we need to make an additional decision, which is to select the subset of schools that yield the highest benefit from collaboration. However, in practice, it is infeasible to consider the combinatorically many subsets of schools to find the optimum combinations. And this inspires us to approach the problem with a model-based estimation. And the learned model will allow the routing problem estimation without high computational cost. And we're able to quickly identify the subset of schools that can benefit from sharing buses and routes. We start by estimating the traveling salesman problem tolerance by an online learning method. And we hope to extend the TSP problem to the school bus routing problem in the future. Well, we can go into...
Just let you know, 1 minute warning.
Okay, great, thank you. So I'm not gonna go into too much detail. We can discuss the details on the breakout room. So I'm just gonna briefly introduce our approach, the online learning. So basically we'll create a digital twin of the road network. In this example is the downtown Pittsburgh road network. So what we do is we distill features from the inner product space of the coordinate vectors. And this vector shown by the X here will be applied to learn a linear model, which learns the optimum TSP tolerance shown by the Y hat. And we'll generate the data in sequence and we'll deploy a gradient descent with mini batch update to sequentially learn the estimation model in an online fashion. And finally, I'll briefly introduce several potential applications for our approaches. So with the solution to the first two problems, we can produce state-of-the-art routing results for school districts. And for the last online learning of TSP problem, we can apply this approach to any road network. As a result, a potential tool is to, given an input of a graph representation of any road network, we can efficiently estimate the traveling salesman problem optimum tolerance. Okay, that's it for me. Thank you everyone for listening.
Okay, thank you so much, Hal.
I'll stop sharing my screen.
Carly?
All right. Hi, everybody. Thank you to all of our presenters. Now we will be using the Zoom breakout feature so you can continue the conversation directly with the presenters. You will soon see a list of presentation topics on the screen and the ability to enter those rooms. Please note the technology does not allow you to choose more than one. So if there are people you are not able to connect with, simply send us a note and we will make an introduction after the session. Okay, Please choose your breakout room.